Welcome to this video on AC waveforms, and in this video we're going to look at several different types of waveform, but one of the most common is the one that we see in front of us here, which is called a sine wave. And we're going to look at some different properties of the sine wave and how they apply to electrical engineering. First of all, we see that one full sine wave follows the pattern that we see in front of us. We have a wave that starts at 0 and increases to a peak and then goes down to what's called a trough and then back to 0 again. So that's one full waveform. So I'll mark some of these terms on here first of all, because this is the peak of our waveform. This is the trough of our waveform. And the distance between our midpoint and the peak is something called the amplitude. So I'll mark that on as well. We can say we've got the amplitude there. And the distance from the start to the end of our full waveform is something called the wavelength. So now that we've marked those important terms on, I want to think more about this wave and what it represents. So let's say that our axes here first of all represent voltage going up the side. So this is a voltage waveform, and time going along the x-axis there. What this means is that in an AC waveform, voltage is always increasing and going positive, and then decreasing and going negative, and then back to the start to repeat again. So the voltage in our circuit, and therefore the current, is actually alternating. It's going back and forward all the time. One of the problems with AC waveforms in electrical engineering is how are we supposed to perform the sorts of calculations we've been doing in previous videos if the voltage is always changing? So one of the solutions to that is to try and come up with a consistent or average value which we can use in our calculations, even though the voltage is taking the form of a sine wave. One of the first solutions might be to take an average of the whole waveform. Well, if we do this for any sine wave, we're going to get an average of 0, which is our center point, which doesn't really help anyone. So one of the solutions is to simply take an average of the first half of the waveform, the positive half here. And if we do that, we get a consistent answer for any given sine wave. The average voltage is equal to 2 over pi times the peak voltage. And the peak voltage is whatever value of voltage we reach at the peak of our waveform. So I'll mark that on there as V pk, the peak voltage there. Now this is helpful because it gives us a consistent voltage that we can use in our calculations, even though the voltage is always changing, like we've said. The problem with the average voltage is that it doesn't quite give us the equivalent power that we would get from the actual sine wave. So a different statistical process is used called the root mean squared, which we don't need to get into in detail in this video, but what we can say is that the root mean squared, or the RMS voltage, gives us a slightly different result, and it's a result that's more accurate and is used more commonly in electrical engineering. So the RMS voltage, which I'm going to call RMS, is not equal to 2 over pi times the peak voltage. It's actually equal to 1 over root 2 times the peak voltage. It's a slightly different result. And what happens is when we calculate the RMS voltage rather than the average voltage, we get a consistent voltage that has equivalent power to the actual AC waveform that we're basing it on. The last thing to mention here is we've talked about peak voltage. But one other term we might hear is the peak-to-peak voltage, and that's a term for the distance from the top to the bottom of the waveform. So for instance, if we have an AC waveform here with a peak voltage of 5 volts, then that means that the voltage at the trough is going to be minus 5 volts. And the peak-to-peak is simply a measurement from the very top to the very bottom of the waveform. So that's the peak-to-peak voltage, and I'll mark that on as PK-PK, V peak to peak, the peak to peak voltage. And in this case, the peak to peak voltage would be 10 volts. We've looked at sine waves in our example there, but there are other types of waveforms as well. Here's an example of one called a triangle wave. And similar to a triangle wave is another type of waveform called a sawtooth wave. Now, one thing to bear in mind is for triangle and sawtooth waves, the average voltage and the RMS voltage are calculated differently to the sine wave that we saw previously. So if you see here, the average voltage is 1/2 or a half times the peak voltage. And the RMS voltage in this case is calculated as 1/√3 times the peak voltage. And that applies to both triangle and sawtooth waves. The last type of waveform that we'll mention is a square wave, which looks like this one here. And here we see actually if we take an average of the first half of our waveform, like we've done in our previous examples, we actually get the same result as the peak voltage, because a square wave is consistently at the peak and then it drops to be consistently at the trough. And so what we see actually is the average voltage is equal to the peak voltage. And likewise for the RMS is equal to the peak voltage as well for a square wave. Let's return back to our example of the sine wave. And again, let's say that this sine wave represents a voltage measured against time. One thing that we might be asked to do is to calculate the voltage at a very particular time. So we might have to calculate the voltage at this point here. Well, if we have a sufficiently detailed graph, we can read the graph to get that value. But one of the things we can do is we can use the formula for a sine wave in order to determine the voltage at any particular time. And that's called the instantaneous value of voltage. And we're going to use a formula that looks like this. It's V, which is our instantaneous value of voltage, which is equal to the peak voltage multiplied by sine 2 pi ft. And t is the time at which we can measure any particular instantaneous value of voltage. So that being said, let's focus our attention on this term F. And F in this case represents frequency. And frequency is measured in hertz. If we don't know the frequency, we can calculate it by using the formula F equals 1/t. And that's a capital T, and T represents the time period. And the time period is simply the amount of time it takes for one full waveform to occur. And we said that one full waveform is what we see here on the screen. We start at the center point, up and down and back to the start again as one full waveform. So the time that takes, measured on the x-axis here, is our time period. I could also rearrange this formula, F equals 1/t, into the form T equals 1/f. So if I don't know the time period, I can calculate it by dividing 1 by the frequency. Let's say that I do know the frequency though, and we're going to have a quick go at an example here. Let's say that we have a sine wave voltage with a peak voltage of 100 volts, and it has a frequency of 50 hertz. And the question is, what is the voltage going to be at exactly 7 milliseconds? Well, to do that, we're going to use the formula that we looked at on the previous slide there. V, the instantaneous value, is equal to the peak voltage, VPK, times sine 2 pi ft. And putting some values in there, we know that the peak voltage is 100, multiplied by sine 2 pi times the frequency, which we said was 50, times by t, which is 7 milliseconds. Now t, as a standard unit, we should express as seconds rather than milliseconds. So I'm going to say 7 times 10 to the minus 3. And calculating that gives me an answer of 3.84 volts. So I'm allowing 7 milliseconds to elapse, and I know that at that exact moment the instantaneous value of voltage is going to be 3.84 volts. Let's have a go at one more question, because the relationships between average voltage, RMS voltage, and peak voltage are the same relationships between average, RMS, and peak current. So here's a question that says that a 10 kilowatt motor is supplied by an AC voltage of 230 volts RMS. And we have two questions here. It says, first of all, what is the RMS current? And second of all, what is the peak current? So the first thing we can do here is we can use our formula for power, which is P equals I times V, but we can rearrange it to say that I equals P over V. Now in this case, it's the RMS voltage, and that means that I'm going to be calculating the RMS current. So let's put some values in here, because we know first of all that the power in this motor, P, is 10 kilowatts, which I need to express in watts, so that's 10,000 watts, divided by the RMS voltage, which is 230 volts. Calculating that gives me an answer of 43.48 amps. Now that we've calculated the RMS current, we can also calculate the peak current. And we're going to use the same relationship that we had between RMS and peak voltage. We can say, first of all, that the RMS current is equal to 1 over root 2 times by the peak current, because we said that the RMS voltage is equal to 1 over root 2 times the peak voltage. So the same relationship applies here. But in this case, we don't want to calculate the RMS current. We know the RMS current. We want to calculate the peak current. And so I can rearrange this formula into the form I peak equals root 2 times by I RMS. And we can say that that's root 2 times the RMS current, which we've just worked out to be 43.48 amps. And that works out as 61.49 amps. So that's our peak current there.